Good morning, everyone. You can, okay. So today we are happy to host Giorgio Volpe, who is a professor in subject matter in the Department of Chemistry of University College of London, so UCL. Before that, he did his PhD at ICFO in Barcelona, and then he did his postdoc at Langevin Institute before joining UCL. So he will talk about actuation, light actuation of soft matter. So the floor is yours.
Thank you very much, Anais, for the introduction and for the invitation. Something that Anais didn't tell you is that actually we met basically 2 years ago. Anais did a small time visiting as a researcher in my lab. And some of the things that are shown in the pictures are actually connected to your stay. So. But yeah, it's nice to be back in Paris. I apologize because I will not be able to give this talk in French. I'm quite happy after having left 10 years ago that I can still order food in French, but that's pretty much what I can do. So I will have to stick to English. And what I will discuss today is work that we're doing in my lab related to active matter. Now, I know that this audience is quite broad, therefore I'm going to start with the basics, defining what active matter is. There might be some of you that already know that and are working with active matter system, but just so that everybody is at the same stage and level, I'm going to start by defining active matter. So what is active matter? You can think of active matter as any system, it can be biological or artificial, which is made up by individual components in units that can take energy from their environment and use it to perform a task autonomously, typically to self-propel. Now, there are a lot of beautiful examples of active matter in the natural world. If you can think about a flock of birds, school of fish, even us, we are an example of active matter if we form crowds. And the idea behind us and how all these other active matter systems that we do need food, energy, in order to be able to do what we do every day. So this is a very simple definition of active matter, but for the people that like physics in the audience, a way in which we can compare and understand active matter system is to compare against what we know. And usually what we know after a university degree is we have a certain understanding of matter that is at equilibrium, so passive matter. And you can think about these systems as a collection of units that are passive units. In my world, these units are usually colloidal in nature, so they're macroscopic. And if you put them in an external driving field, like a potential, they can self-assemble to form structures that can be functional. For example, if you think about colloids, colloids tend to be of a size that is comparable with visible light, and because of this they can form colloidal crystals that are photonic crystals that have an optical band gap, and therefore they can interact strongly with light. What is the problem with this matter near thermodynamic equilibrium that is passive? So usually the structures that you obtain tend to be static and not very reconfigurable. So both the structure and the function are static most often. It's different for active matter. So if you have a system that is out of equilibrium, so they can actively exploit energy in the environment to drive itself out of equilibrium, and you can think, for example, at the case of life, where you have systems that can be made up by active components like biological cells and passive components, minerals, for example, and they can form tissue which is very different in terms of function and structure from matter that is at the thermodynamic equilibrium. For example, you can think about bone. It's usually tissue that is made up by cells, osteoclasts and osteoblasts, that are continuously competing against each other to restructure the bone matrix, which is made of minerals. And this happens in the presence of energy, food, which drives the whole process. But because of this very dynamic nature of the process, the structure and the function of the material is extremely adaptive, dynamic, and reconfigurable. And that's why, we can go through life with different level of activities, gaining or losing weight. Especially as an Italian, I will gain a lot of weight after the Christmas holidays, which then I take a couple of years to lose, so it never goes back the way it came from. But all of this means that because of these processes that are happening naturally within our body, tissue can adapt to our life changing style. In my case, I'm particularly interested in synthetic active matter. We do some work with biological active matter, mainly bacteria, but I'm more interested in developing synthetic systems that can reproduce these natural behaviors. And for me, there is a very good energy source that we can use to drive this sort of synthetic active system, which is light. Why? Well, first of all, light can be biocompatible, so you can think about interfacing with a lot of biological systems, but it's also broadly available. You can have it because of natural sunlight, but also in the labs nowadays with lasers, light is relatively cheap energy source that we can obtain, use, and control to a very high degrees of freedom. If you think about systems that are active, that exploit light, you can find them at all scales, starting from the molecular scales, like molecular motors that can twist, translate, rotate, thanks to light. And this was actually part of the reason why Feringa and other people a few years ago got the Nobel Prize in developing molecular motors. You can jump to the opposite scale and you can think about macroscopic antimatter, where there are robots, like our size robots, that exploit sunlight, for example, to drive their own processes. Where I'm more interested is this intermediate regime, where you can find soft-acting matter, so a mesoscopic scale between the micron to the millimeter scale, where you can find a lot of systems that are also driven by light. Obviously, colloidal particles, microscopic particles. You can also have droplets, human engineered bacteria that can make beautiful pictures responding to light, and even millimeter-sized microrobots that take light to move. Now, if you think about this mesoscopic scale, especially compared to the nano and the micro scale, there has been a lot of beautiful research that happened over the last 15, 20 years. But in terms of actually functionalities that can achieve out of this system, we're still quite limited. So what I'm going to do during this talk, I'm going to give you 3 examples from the lab where we started to think a bit more about making these active colloidal systems functional. We're still far from real-life applications, but hopefully by the end of the talk you will see how we are trying to make a step closer from fundamental science to more real-life applications. And I'm going to show you 3 examples. First, how we can make optical materials out of active colloids, and in particular I will show you the case of a laser. Then how we can use these systems to make printed materials that are 4-dimensional, so they can form in 3D but also in time. And finally, how we can start to create systems of active colloidal particles that are closer to natural social intelligence that you will find, for example, in societies of insects like ants and termites. But let's start with the first case. I guess probably many of you know what a laser is. You might use it in your own research. You might have to use it when you check out at the supermarket or you want to take a flight. Lasers are really endemic in our society, and they really can span in many different sizes and shapes. You can have very small ones like this laser pointer. The laser inside this laser pointer is probably really, really tiny in the order of millimeters. Or you can have like gigantic one, like this monster laser lab that is obviously the size of a human person, if not larger. Now, whether you think about the laser pointer or this monster version of it, or the one that you might have in your lab, usually you will be working with a conventional laser. What is a conventional laser? It's a laser in which you have 2 mirrors that make a cavity containing a gain medium, and light is being bounced back and forth between these 2 mirrors and is being amplified as it goes through by the gain medium. As a consequence, there are more photons that are identical that are emitted, and because one of the 2 mirrors has a very tiny percentage of light that can leak out of it, we're talking about 1%, you can end up with a laser that comes out of the cavity, which is typically a very nice, clean Gaussian mode at TM00. But think about it. this is 1% of the power that is actually being generated inside the cavity, okay? So we're really talking about a small fraction of the power inside the cavity. But most of the lasers that you will be facing in your everyday life will probably belong to this sort of category. Now, I know because I've been working here before that there are a lot of people in Paris that are working with non-conventional lasers. So if anybody in the audience is working with non-conventional lasers, you probably already know about the fact that there are a class of lasers that are not really falling in this category. And one of the most common and famous one is known as the random laser. What is a random laser? Well, you still have the gain medium because you need to amplify light. But in a random laser, there is not a cavity as such, so you don't have two mirrors. You have many individual tiny particles that each one of them can scatter light. If you do this strongly, many times, you can confine light within this random material long enough for it to be amplified, and the modes that will leak out and that you can measure will have some properties common to a normal lasers, but their modes will be more chaotic, more random. You can have modes that are extremely localized, so they're very confined in space and time, or you can have modes that spread out over the whole structures. But fundamentally, they don't fall within this beautiful standard image of conventional lasing. Now, whether you're thinking about conventional lasers or random lasers or other unconventional lasers, most of these devices tend to be static and they're not reconfigurable. What we wanted to do is to see whether we can take inspiration from this biological picture where you have very adaptive materials and see whether we could recreate something similar in the photonic world. So as here you have a combination of active and passive units that in the presence of energy can form a functional structural material that is reconfigurable. What we did is to combine two types of colloidal particles. Some are active, these Janus particles. Some are passive, these Titana particles. I will tell you a bit more about them in a second. And in the presence of external light as an energy source, we were able to create reconfigurable random clusters of these particles that in the presence of a gain medium could laze. And we were able to probe that by doing spectroscopy on the optical properties of the material. Okay, this is the pitch. I'm gonna show you step by step what we actually did. To make our random laser with our active matter system, we need three key ingredients. One is an active colloidal particle. So this is the particle that drives the whole system out of equilibrium. It's the one that can convert external energy into energy for the system to be used to do something useful out of it. We need gain, because without gain there is no amplification of light. And we need this scattering medium that can confine the light that is being amplified within the material long enough to achieve lasing properties. So in terms of active particle, we use a Janus particles. What is a Janus particle? It's a tiny microscopic particles that is half covered in a light absorbing material. It can be a metal. In our case, it was carbon. Because of this asymmetry, and Janus, if there is any Italian in the room, you will know that Janus was one of the Roman gods that had two faces, one looking at the future, one looking at the past. And that's why these particles have this name. It's inspired by this Roman god. And because of the symmetries, if you provide light, only the half of it that can absorb it, the metallic or carbon-coated one, will heat up, and this can lead to self-propulsion. For a lot of the things that I will show you today, you don't need to have a Janus particle. You could have another absorbing element, okay? But there are some aspects of what I will show you today where actually having Janus particles is important, and I will point them to you as we go along. You need gain, so you need like something that can amplify the photons. For that, we use a laser dye, rhodamine. Why? Because it's a well-characterized laser dye. It is used in many real applications of lasers as a very well-characterized optical absorption and emission spectra, and also the lasing properties of the dyes are extremely known. We didn't want to engineer the dye, we just wanted to show that it's possible to make a laser out of this system. And finally, we needed a scattering medium, something that can scatter light strongly enough for it to be confined within the medium as long as needed for it to be amplified as a laser. We use titanium colloids for two reasons, actually for three reasons. One I didn't put on the slide. A, they are commercial, so you can buy them. B, they have a high refractive index. And C, you can buy them in a size that is comparable to the wavelength of light. Because of these two last properties, it means they can strongly interact with light, they can strongly scatter it. You can be in a regime of multiple scattering, which means that the photons will really be trapped within the medium and they can be amplified by the gain medium before they leak out of the structure. So now that we introduced the three components, let's see how the actual material looks like. It's as simple as a microfluidic chip where you have colloidal particles. The big chunky one in the middle is the Janus particle, the one that is driving the system out of equilibrium. And then you have many titanium particles that are dispersed in a solution of rhodamine dye. Without the external energy source, light, to trigger the response to the Janus particles, all of these particles are moving because of Brownian motion. As soon as we provide the external source for the Janus particles, you can see that all the titanium particles collect around the Janus particle, forming these random looking clusters. And of course, you can revert this by removing the illumination light for the Janus particles. The particles disperse and because they go back being Brownian. We can actually understand this with a very simple model in which we consider the Janus particle as a heating element. So it generates a temperature profile. So this is a heat source. The temperature will decrease as you move away from it radially. And because of this heat source, the titanium particle will see a velocity field caused by the flow of the liquid because of the temperature gradient. And because of this very simple model, we could actually reproduce quite well the experimental data. What you see here with the shaded areas are the experiments. You have the accumulation of the particles, so the number of particles accumulating around the Janus over time. If you remove the energy source, you have the dispersal, and then you can iterate this back and forth. Yes?
The heat source is symmetric.
Sorry?
Right? The heat source is symmetric despite its non-symmetric.
It's symmetric because the Janus particle, once they, if you notice here, you can see the cap, you can see an asymmetry here. As soon as the Janus particles are in the cluster, they will face downwards because the carbon side is heavier. So then there is, if they're not free to move, they tend to reorient against gravity.
So it's not a symmetric.
No, that's why I was saying that for a lot of the things I will show today, you can even think to have another heat source. It could be like a particle absorbing dyes. In this case, you could do without, but there is one case that I will show you in a couple of slides where the Janus particles are free to move and they take the cloud of titanium particles with them until they merge into a bigger laser system. In that case, you need the motility. But for everything up to that point, you could take Janus particle and change for absorbing sphere. Okay?
Say energy off and on, what are you switching off and on? Light, heat? Or
It's a light source. So it's a light source that the Janus particle can absorb, but it doesn't affect we are basically having two light sources at one is the one that triggers the Janus particle and it's in a red laser light, which is not absorbed by the rhodamine.
Yeah.
And then we have a nanosecond laser in the green, which is the one that is pumping the rhodamine. And yes, yes, but the two are not interfering with each other. Okay.
Well, sorry. What's the mechanism for your relation between the devastation and the temperature?
It's called thermosmosis. So if you probably know thermophoresis. It's no? Okay, so let's forget about thermophoresis. Thermosmosis is much simpler actually. So if you have a substrate and you have liquid near the substrate and there is a temperature gradient, there is an enthalpy contribution coming from the fact that the liquid molecule are near the substrate that they don't have if they're in bulk because of the difference in interfacial energy. In the presence of the enthalpy contribution and the temperature gradient, the liquid will flow towards the hot part. So in this case, towards the Janus particle. And anything that is dispersing it will follow this velocity field. But it's basically coming from the, so you need a substrate and you need a temperature gradient. If you have these two conditions, there is a change in chemical potential, which drives the liquid towards the hot. Yeah? Yes? This one is just a constant for our system. It depends on the material properties. It's basically a ratio between the diffusivity of the particle and the thermal diffusivity of the particle. So the Brownian diffusivity and the thermal diffusivity, and depends on the material. It's called motility. It's usually something that you will have to determine experimentally. There is some theory behind it, but it doesn't always match reality. In this case, we actually estimated it from material properties. So it's not fitted. But it doesn't necessarily always work that your system, from the material properties, you can estimate the motility well compared to the experiments. But in this case, it was estimated from material properties. No.
You say that the liquid is attracted by the particle, but somehow you have
By the gradient of temperature, by the
Sure, it cannot accumulate. So do you have like
it will recirculate.
yeah, okay.
So it's a chamber.
Okay.
So the liquid itself will recirculate, but the particles are heavier. So then they.
So the image I see
No, and actually, I don't know if you can see that, but if you look near the Janus particle, it doesn't look like a monolayer. It starts to see like a bit of accumulation of, but it's not enough to break the geometry for us. Any other question? No? Okay, so once you have this system that works, this is only explaining why we can have a reconfigurable material. It doesn't explain the optical properties. So what you can do is to solve the radiative transfer equation for light within the material as a function of two parameters: the density of the particles, the titania particles that you have in the system, and the critical radius of your system. So the geometry, imagine it like a circle. There will be the radius of the circle, and there will be the density of scatterers that you have within the circle. If you solve the equation, you can find two areas. The blue for low particle density and small radii, and this is a no lasing area, blue. Then you have the area where at high radii, so larger structures with a lot of density, you can lase, and this white line here is the threshold between no lasing and lasing. If you cross this threshold, you can go from lasing to no lasing and vice versa. So if you can do this reconfigurably, you are basically having a system of colloidal particles that breathe, and they can move from being a laser and not, and vice versa. And these are the experiments which actually reproduce decently well what we expected from theory. And what we're doing the experiments by providing this energy source for the Janus particles, for the absorbing element, is to drive the accumulation of the titania particle from the low dense area where you shouldn't expect any lasing to the high dense area where you should expect lasing, and vice versa. So this is what happens. You are accumulating the titania particles around the Janus, and the line width of your spectral properties is reducing in a nonlinear way, going from a no fluorescent lasing system to a lasing system. And you can see it by measuring actual spectra. So the blue here at the bottom is the fluorescence of rhodamine before you accumulate particles. If you accumulate them, a very sharp peak will start to appear, and this transition from fluorescence to sharp peak happens in a nonlinear way, both in terms of pump fluence, but also in line width, which is characteristic of lasing properties. If you then disperse your particles because you are removing the energy source for the heating Janus particle element, you go back to a fluorescent spectrum, and you can reaccumulate going back to lasing and continue like this. You can pretty much have something that breathes based on this availability of external energy that is self-driving, accumulation and lasing properties, or dispersing them. So what can you do now with this system that you can't do with a conventional laser? You can do an optical switch in a microfluidic chamber where you can switch the lasing in time and space. For example, if you have two of these absorbing elements, you can decide around which to accumulate the titanium particles, and you can transfer the cargo or scatterers to the other Janus particle, and so on. So you can pretty much switch the lasing actions in space and time. And here you can see the experiments. If we're illuminating this particle on your left, you get a cloud of titanium particles accumulating here, transferring to the particle on your right if you're illuminating only that one, and back to the one on your left if you switch the illumination. And you can see that you're starting from a situation where both areas are fluorescent, non lasing. If you're accumulating around the particle on your left, you get a narrowing of the spectral properties, so lasing, and you can do this iteratively between the two particles. Now, up to this point, as I said, you can do everything I told you, substituting Janus particle for absorbing element. However, this example is one where you actually need the motility of the Janus particle. What you see here are 3 Janus particles. One has already accumulated some scatterers, but the amount of particles that you have there is not enough to see lasing. So at this point, we are below the lasing threshold. However, more Janus particles can move towards this cloud, taking more titanium particles with them, increasing the size and the density of the system until you cross the threshold and you go to a more lasing system. In this case, you do need the Janus particle. Everything that I told you until now, up to this point, you didn't. You could have substituted Janus particle for any other absorbing element. And of course, because of this, you can also make shapes out of fun, nothing else, but you can make a glass hour shape, triangle, squares, and this is because you are making these particles self-assemble cooperatively to a point in which you will see lasing behavior from these different shapes.
So how do they move here? Because you said the axis is out of the plane here, and they move in the plane.
Yes, so their cap, so their asymmetry is parallel to the plane. So you will have like a cap on one side. The plane is here, the cap is here. They warm up, and that creates a temperature gradient around the particle, and they move in this temperature gradient. And while they move, they also accumulate titanium for the same reason that I showed you before. By this point, because they're moving, they take them with them until they join a bigger cluster. At some point, they become immobile because there is too much mass around them to be able to move. But up to that point, they can move and carry stuff with them. Okay, so I'm gonna now switch gear if there are no other questions on the first part. I'm happy to take questions as we go along, so if you have questions, just ask, as you have been doing. The second example is quite different in the sense we're not working with colloidal particles, but we're working with the droplets. And the system that we're working with now is a liquid-liquid interface. You have water at the bottom, oil at the top, and you have these water, ethanol, binary droplets that are here at the interface. The interface is stabilized by 2 molecules, cellulose nanocrystals and PDMS. They form a monolayer at the interface. Now I'm going to show you a video, and I want you to pay attention and tell me if you find something strange about this. This is a water droplet that drops. As I said, this is water-based, this is water, and this is oil. I'm going to play it again. Is anything strange for you there, or you say it's the normal thing that you would expect for it to happen? You are dropping a water droplet on water. They're not coalescing with each other, right? For me, it's strange. So obviously, there is another thing that you might want to notice. The interface is behaving like a trampoline. So this stabilizing layer is really changing the property of the system. The interface, and that's a claim that I'm gonna confirm later with data, is behaving like a solid, okay? And because of that, the droplet doesn't coalesce with its own water phase, and the interface itself has elasticity. Now, if you put multiple droplets, they self-assemble. Why? Because you can think that they form a potential well common to the three of them, and they go to the minimum. There is nothing new in what I'm telling you now. You probably already know this by capillarity. And if you love Cheerios for breakfast, you probably experience it as you're having breakfast. If you put Cheerios on milk at the milk air interface, they will form clumps for the same reason. There is also these water striders. These are some insects that you see gliding on water in lakes. They're exploiting this capillarity to move, and they don't sink because of the same reason. So there is nothing new in the actual effect, but the physics of the effect is slightly modified by the interface, and I'm going to show you how. Think about two droplets that are attracting each other through this interface. You can consider this a balance of forces where you have this capillarity, and then you have some viscosity that is preventing the motion of the droplet. You can think about two components. One is the stock component coming from the drag of the liquid. These droplets are suspended in a liquid. And then you can add another viscosity term that depends on the surface. My hypothesis is that it behaves like a solid. So there are these two terms to the friction that should counteract capillarity. If you now take the standard approach of capillarity theory, you would assume that the stock drag is much greater than the viscous drag at the interface. You can neglect the second one. You should expect that the velocity changes as the two particles, the two droplets are approaching, with a fifth power of the size of the droplet. If you instead say that the one that is dominating is the viscous drag at the interface rather than the stock effect, then you can do the math, and what you should expect is that the scaling should be with the fourth power of the droplet. So to test whether it's one or the other case, we did a lot of experiments where we'll measure the velocity of attraction between two droplets as a function of the inverse of the separation distance. We changed the size of the droplet, we changed the composition of the droplets, so changing the mass basically. And you can plot all of these experiments if you extract the slope of these lines into one master curve, which shows a fourth power scaling. So our idea that this behaving like a solid, therefore has a non-negligible viscosity that is affecting the droplet motion, is actually correct. And this is really important because everything that I'm going to show you now that we can do with the system is because of the presence of this very, very thin layer of molecules, a monolayer, but is enough to change the property of a liquid into a solid. Okay? So obviously this is something you can do because you have this attraction from the capillarity, but also because the droplets are stabilized by the interface. This is, for example, what happens as you change the composition of the droplets in terms of mole fraction of ethanol versus water. You can see that this is the droplet lifetime on the interface, so before it coalesces. The reason why we stopped at 1 hour is not because it coalesced, it's just because the PhD student had a limited amount of time to finish her thesis, and obviously these droplets were stable sometimes for weeks, and we thought that 1 hour was a good experimental time to prove what we wanted to prove. Only if you reduce the ethanol percentage to very small amounts or really high amounts, then you see coalescence. So if you really have a pure water droplet, it will coalesce with the water phase. But as soon as you have like maybe 10% of ethanol up to about 80% of ethanol, it will not coalesce. Only if you have pure ethanol droplets, then it will coalesce again, and that's because ethanol will disrupt the monolayer eventually. Not only they are resilient against coalescence with the underlying water interface, they can also resist coalescence against each other. And that is really happening for a very long experimental time, about 1 hour, in this regime where you have a very small amount of ethanol in the droplets. So mainly water, up to 20% ethanol. They can be stable in other regions, but this is where the stability is really the strongest. So because of that, you can print droplets, and they will attract each other, they will self-assemble, and the self-assemble that you obtain, the structure that you obtain, will depend on the properties of the droplets. If you have monodispersed droplets, they will form hexagonal packing. If you have bidispersed droplets, they can form square packing. But you can do more. You can include materials in these droplets because they are liquid. Here, for example, we included rhodamine dye. That's why they look red, some of them. And of course, depending on which light you are, wavelength you're looking at, you can see the rhodamine or not. So you could potentially think about encrypting information in this system.
Can you comment on the tracks?
These ones. Yes, so there is a bit of, you have to think that you have at an interface of water and oil. And there is some seeping through the interface of material. These are like tiny droplets that are forming, and once the droplets passes, it collects them. Eventually, it will rehomogenize.
Are the droplets decorated with oil eventually?
Sorry?
Are they taking oil from the substrate?
No, we don't think so. They're losing material to the substrate, to the oil phase. I think the ethanol is leaking to the oil eventually. That's why they're shrinking in size. But if you see here, the trace is very clear. It starts to fade again as you wait more time. I think this is a well-known fact that you have like tiny, it's like it from an emulsion, spontaneous emulsification of the interface. And that's made even worse by the fact that you have this monolayer that it stabilizes. So there are a lot of studies done with emulsions where if you have a surfactant, which in our case will be this PDMS, and ethanol, alcohol, it actually makes them more stable. So yeah, so I don't think it's fully understood why, but the kind of within a regime of quantities, they have like an enhancing effect to stabilization. And that's the same that we saw here. Any other question? No? Now, because I said that we can put rhodamine. Rhodamine is fluorescent, which means that if you look from an angle, you can also see a fluorescent pattern. This is the logo of my university. I've been trying to get money from the provost for a long time by making logos in all form of shapes. Still never managed, but I'll keep trying. But what is also astonishing for us is the fact that this, again, it's a monolayer of molecules at the interface. You can actually build multiple layers of these droplets with thousands of droplets, and they're stable, they don't coalesce. Every time I think that this is actually mediated by a single layer of molecules, I find it fascinating because it will not be my intuitive picture. So you can actually build multiple layers of droplets if you wanted, for example, to use it as a way to do some tissue engineering, and it will be stable.
Is the trampoline sagging more and more as you add the plate?
Eventually, it will stiffen up. So something that people study with these sort of layers, depending on the pressure that you put from the outskirts, you also change the mechanical properties, so it becomes stiffer. So eventually, I think it will break before keep on bending more. Eventually.
Cannot be a way to measure the weight of your.
Maybe, but we haven't thought about that. But maybe yes. So in the talk I said light, right? There is no light here. Well, the beautiful thing about this interface is that you actually can make them in very different ways. For example, you can add particles like gold particles to this monolayer, and that will change the response. Gold absorbs strongly at 532 nanometers because of plasmonic properties, which means that if you have a interface that is now also including these gold nanoparticles and you shine light on it, you can attract the droplets because of these thermal effects. caused by the absorption of light by the gold nanoparticles. And these effects are strong enough to actually move entire structures. So this is where we're at with this work, but I think by combining this capillarity with this external light-induced control, you probably can have a lot of flexibility in what sort of structures you can achieve and the properties and the functionality you can embed them with. Any other question on this part? Am I doing with time? Yeah? No? So the last example that I want to show you is, again, jumping back now to colloidal particles. But in this case, I'm thinking about the functionality that is very different from the kind of material property that I've shown you about. I've shown you optical properties, printing. This is maybe thinking more about intelligence, social intelligence. And in particular, I'm thinking about one type of intelligence, stigmergy. You guys know the meaning? Well, this term was actually created by a French biologist, Grasset. He was studying the behavior of termites, and he found that termites can, even being very simple, they can somehow manage to communicate with each other through the environment to coordinate very complex behaviors. This is stigmergy, indirect coordination and communication mediated through the environment. It's not direct communication like the one we're having. I'm talking to you, you're talking back to me. This is direct communication. This is indirect because the termites or other social insects will leave traces in the environment for others to pick and change their behavior, even though they don't really know what is the bigger picture. Now, there are examples of stigmergy at many scales and many systems. Social insects, ants, termites, bees, wasps, they all respond to a form of stigmergy. That's why they're social, they can communicate through the environment. Robots have been designed inspired to these animals to respond to very simple rules, but still be able to create complex systems. For example, build structures by responding to very simple rules. And when Anais was visiting, I took her to show this park near where I live, and always been fascinated by the creation of these paths, which are obviously not meant to be there. There should be grass there, but people, by walking on them, they kill the grass and they leave traces for the new hikers to follow, and you do it without thinking about it. But this is not by design, this is a form of stigmergy. You follow the path for low resistance because it's been already laid out for you. So what we wanted to see whether you can have similar behaviors with very simple system made by active colloids. You can't program them too much. There is no machinery, there is no computing, processing unit with them. They're, as I said, they're Janus particles. They can only absorb light and use it to propel. Now, the system that I'm showing you here is slightly different from the one with the random laser. In that case, we had Janus particles in an ethanol solution. Here we're working with a water lutidine solution. Water is water, lutidine is a holy substance. What is nice about this solution is that there's an upper critical point, which means that below a certain temperature, the two are completely miscible, so they form one phase. Above this critical temperature, the phase separate into a water-rich and a lutidine-rich phase. And we play with that effect by locally inducing, thanks to the absorption from the cap of the Janus particle, the water lutidine mixture to cross this critical point and phase separate around the Janus particle. Because of this phase separation, there is an asymmetry that causes the particle to move because of diffusion phoresis. Now, this is a video, and I want you to observe it carefully, where I'm going to play it again. We have the Janus particles that have been traced, and all of these are just passive Brownian colloids of similar size and material. The only difference is that they don't have the carbon cap. Can you see anything strange happening here?
The binary star.
A binary star? You mean this one?
Yeah.
That's kind of making like an engine, a rotating engine. That's not the effect we were after. But I think this one and this one were kind of stuck on one side and they kept on going around But even if you look at that one, what is it doing as it's kind of digging a channel for itself. Now, if look at these two particles, this one is propelling and digging a channel. This one is exploiting it. Very lazy particle that follows after the previous one, right? And for me, when I saw it, this is similar to what we do as we, go for a nice walk in a nice park. We follow the path of low resistance. So maybe there was something about stigmergy happening here. So we tried to quantify this better. And one of the things we had to understand is that these paths are being laid and are being reused. What is the reason for this reuse? You need to think about the mechanism of how this particle propel. If you are in bulk, you have this phase separation happening around the Janus particle, where you have a water-rich and a water-rich and a lutein-rich phase, and that causes propulsion. As soon as you put one of these obstacles near the Janus particle, you create an asymmetry in the demixing. This asymmetry generates a torque, which makes the particle deflect from the obstacle in our case. So as the particle comes moving straight, crossing the obstacle, there is an asymmetry demixing left to right, which makes the particle deflect. And you can look at many of these events and you can actually measure this deflection angle. So you can see that on average, the particle will move away from the obstacle. So if you think about a sea of these obstacles, you can think that if the particle is approaching two obstacles head-on, symmetrically, whatever reduction in the mixing happens will be symmetrical too. The particle moves straight, it digs a channel. And that's what's happening here. It pushes through these two particles and it opens a channel. However, this particle, then there is a already laid out channel. And what you see once it arrives here with a slight tilt, because of this asymmetric demixing caused by these obstacles, it will actually align with the channel and continues to reuse it. So there is this form of communication happening from the environment where by chance a particle leaves an open channel for another particle to then reuse through this feedback mechanism. The particles, without knowing it, are communicating from the environment, and this is changing the behavior of the system. What happens, for example, look here, you have multiple particles that are following each other. This one is the one that is putting the effort to create a new channel because it faces a wall of passive particles. The other are very happily reusing it, and eventually they catch up with the front runner because the front runner is putting effort to dig a path for itself, so it's slowing down. The others find a path of no resistance, they can catch up quickly. If you want, it's like when bicycle, they shouldn't do it, but they follow cars to get less wind resistance. It's a similar thing. And because they catch up with each other, they end up forming groups. And what we found that was really interesting is that the size of the groups tend to be stronger, higher at intermediate density of obstacles. Now, this is again something that I found counterintuitive once we found it. If I think about a particle moving through obstacles, my intuitive picture would be that it will struggle to move through more obstacles. It will slow down. It will find it more difficult to move through them as you increase the density. However, there are these paths being laid out, which somehow reduces this behavior. Particles can reuse this path. They can find each other faster at an intermediate range of obstacles before the naive picture of the resistance coming from the obstacles kicks in. If you have too many obstacles, the particles are pretty much trapped. They can't escape their local environment. They can't find each other better. But if you have an intermediate regime where the particle can leave trails and reuse them, then they can actually form bigger groups. And you can see it here. As you increase the density of the passive particles, there will always be an optimal behavior in terms of group formation at these intermediate regimes. Why? Because they can leave and reuse these paths. Now, we try to understand this a bit better in looking at the kinetics of this group formation. These are simulations, they're not experiments. You can think if you neglect fragmentation, which doesn't happen often in our system, once the groups are formed, they tend to stick for a long time. you can think about aggregation happening through 3 times. You can have 2 monomers, 2 individual particles joining and forming a group. You can have a monomer joining an existing group, or you can have 2 groups merging together. These are only the 3 aggregation dynamics can happen. And again, we're neglecting fragmentation because in our system doesn't happen on a reasonable time scale. So if you write down the kinetics, you have the kinetics for the monomer. A monomer can only disappear by either 2 monomers joining a group, or 2 monomers forming a group, or 1 monomer joining an existing group. There is no fragmentation. Monomers can be put back into the system. If you look at the groups dynamic, groups can change because either there is a new form by 2 monomers joining, or because 2 groups merge into one, so there is one that disappears from the system. And if you look at these rate coefficients and you simulate them and you try to find them the numerical values as they change with the density, what you see is something interesting. That the 2 that show the same non-monotonic trend that I shown you in the experiments are the monomer joining a group and 2 groups aggregating, not 2 monomers forming a group, which means that the dynamics that you are seeing are the groups themselves catalyzing their own growth. And that's where there is coordination. Obviously, you will need 2 monomers at some point to meet and form a group, but those are not the leading dynamics. The leading dynamics is once the groups are formed, they will keep on growing. Okay, they will keep on accumulating particles, either by an additional more monomers or by joining to a bigger cluster. Important, if you get rid of that torque, you go back into the naive picture where the higher the density and the more the resistance to the motion, no groups tend to form. And that becomes worse and worse as you increase the density of passive particles because they struggle to move through obstacles, as you would expect. So to conclude, what I show you is some work that we're doing in the lab to try to make this active matter at the macro scale a bit more functional. We're still far from real-life applications, but I show you that you can make an optical material, you can print these systems and make something out of it, and you can start to recreate behaviors that we see in terms of social intelligence in nature. Now, this is a bigger trend than what we're doing in the lab. There are this new concept of animate materials where you want to make materials that are active, adaptive, and autonomous. And people are trying to do it at very different scales, from real architectures where you have living buildings to robotic systems and down to my scale where you can use active particles that are colloidal or liquid in nature to make systems. And obviously, if you look at how the things have been developed, you will find that at the bigger end of the scale, things are more active, autonomous, and adaptive because we can easily make them capable of processing information thanks to computers and so on. As you move down to the smaller scales, the challenge is how can you achieve intelligent-like behavior, keeping the processing capability to the minimum because we don't have that capability to create complex machinery as biology does within cells yet. But I think that there is definitely scope to make materials that are a bit more active, a bit more adaptive, a bit more autonomous. And ultimately, if you join efforts across the scales, hopefully we can also make materials that are more sustainable for a better future for everybody, from humans to technology. And finally, I would like to thank the people in the group, particularly Manish, Anshu, and Rob, that are the one behind the work that I presented today, and you for your attention, for the many interesting questions that you raised.
Thank you, Giorgio. We already had a lot of questions, but is there any questions? Maybe 1 or 2? You're good? Okay.
Thank you for your presentation. Can you come back to the formulation of the thermophoretic speed?
Which?
Or, you know, the one that
for the laser?
at the beginning.
Yeah.
Can you show the?
Yeah.
I might be wrong. I'm not that familiar with this, but if I remember well, in the coefficient at scale, the effect of your thermal gradient, there is a matter of ratio between the thermal conductivity of your
Yeah, that's absorbed in this
yeah.
coefficient.
Yeah. So did you select? My question is, did you select the particle for this reason, or for
Not really. We didn't try to optimize the system for the thermal effects because we were trying to optimize it for the optical effects. But you could try to optimize it for the thermal effects. One simple change you can make is to work in water rather than ethanol. But then you need to find a dye that is happy in water, which rhodamine will not be as much, and that can also lase as well as rhodamine. So we didn't try to optimize the thermal effects. And if you notice, the accumulation is quite slow. You know, this is probably 30 minutes at the beginning. So we're not really fast. And again, part of the reason is that the thermal effects were relatively weak for our system, as we had to boost the optical ones.
The question? I had a question about the torque, the difference of torque due to the presence of the obstacle. But in your case, you have a lot of obstacles, or you have a wall of obstacles. So how does it modify the torque in turn? You see?
You mean in the last?
Yes, in the last part, because you show that there is a torque induced by the presence of one obstacle, but does it change anything if you're...
Yeah, so the torque that I've shown you, actually it's already calculated from the presence of the multiple obstacles.
Okay, okay.
So I think that's why you have a spread.
Okay, so that...
Yeah. But we don't know from fully experimentally because it's not easy to measure, but from the model we developed, we assume that the torque is additive. So if you have, so it will depend from the number of obstacles,
yes,
but also from the distance of the obstacles.
Okay.
And with that, we were able to reproduce the experiments quite well.
Okay, so you have a law on the torque.
Yeah, it will. The more obstacles and the closer the obstacles, the stronger the torque will be.
Okay. Okay. Good.
But this is already measured from the experimental data with the many particles.
With the many this is in the full system.
Yeah.
Okay.
So we looked at the individual active particles, but in the full system.
Okay.
And there is a spread, which I guess is coming from the fact that
Okay, thank you. So let's thank Giorgio again. And Giorgio is here this afternoon, so feel free to contact me if you want to discuss with him. Thanks.